The Newtonian conceptual apparatus, the concept of force in particular, was also essentially extended in different yet related ways in the investigating of so-called constraints, especially the constraint of rigidity by, among others, Heinrich Hertz. Profound conceptual problems accompanied these extensions of the concept of force and other classical concepts, and led to puzzling shifts and anomalies in the behavior of the relevant classical concepts, especially when applied to macroscopic matter, as opposed to point particles. The upshot on Wilson's telling is that the concepts of classical Newtonian mechanics did not form a self-sufficient system when applied to this domain. Aside from the traditional mechanical concepts, force, mass, and so on, alien concepts from outside mechanics proper, concepts belonging to chemistry and thermodynamics, for example, proved to be absolutely indispensable as well. The classical description of macroscopic matter thereby showed itself to be no self-sufficient and self-consistent theory at all, but rather what Wilson very helpfully calls a theory facade, a makeshift patchwork of mathematical descriptive devices sitting on top of the true, as far as we now know, microscopic reality described by quantum theory. Much as the true spherical shape of the Earth can be described by a patchwork or atlas of flat two-dimensional maps related to this true spherical shape by a variety of different mathematical projections. So now see on the page that isn't the quotations, there's a page with the two pictures on it. The top page is Wilson's picture of how the classical facade, the different patches of it, sit on top of the underlying quantum law. And it is precisely this situation that underlies Wilson's anti-Kuhnian and pro-scientific realist diagnosis of the dispute between Duhem and Kelvin, remarked upon in the quotation number 5 above here. That's what they were struggling with. Neither Duhem nor Kelvin had any idea that classical mechanics was a theory facade sitting on top of quantum mechanics, and their different responses, one a kind of realistic mechanism at the hands of Kelvin, or a seemingly instrumentalistic, anti-mechanistic view of Duhem, are two different responses, neither of which quite understands the situation. That's how Wilson is this. Both of which are understandable, and neither is a paradigm out of the mindset. We are now in a position to understand more precisely why Wilson has difficulties with the Hilbertian notion of implicit definition, particularly when taken as a complete explanation of the meanings of the fundamental concepts of mathematical physics. Indeed, as Wilson points out, Hilbert included a successful axiomatization of classical mechanics as a desideratum in his list of famous problems. And what we now see on Wilson's account is that no such self-sufficient axiomatization is possible for classical mechanics. There is no such thing. Classical mechanics is simply a collection of local patches of mathematical representation constituting an atlas-like theory facade. It is not something that could possibly be organized as an axiomatic theory at all. In this case, the whole idea of a complete system of implicit definitions delineating a Kuhnian paradigm or conceptual framework called classical mechanics makes no sense. And there is nothing that characterizes what we might call the full space of possibilities allowed by classical mechanics, the set of classical mechanical possible worlds. It might appear, therefore, that if we truly want to understand the conceptual pressures leading to the breakdown of classical physics at the turn of the 20th century, from the 19th to the 20th, we should abandon Kuhn, along with all other neo-Kantian projects, and embrace the robust scientific realism underlying Wilson's detailed and delicately filigreed accounts of actual word-world correlations, as in this case. My response to this last suggestion, that is abandoning Kuhn, abandoning all neo-Kantianism, is that the conceptual pressures emphasized in Wilson's account, those having to do with the relationship between classical mechanical molecular theory and the behavior of macroscopic matter, are not the only factors leading to the breakdown of classical physics at the turn of the century. My Dynamics of Reason project focuses on a rather different and orthogonal set of developments concerning the relationship between our fundamental mechanical concepts of space, time, and motion and the empirical phenomena they aim to describe. Namely, first and foremost, the observable, purely relative motions we actually experience in the world around us. The problem engendered by the Newtonian concepts of absolute space-time and motion in particular did not concern the relationship between macroscopic matter and its microscopic constitution. The problem was rather that absolute space-time and motion, as Newton characterizes them in the Scholium, appear not to be part of the empirical or phenomenal world at all. They have no possible causal relation to our senses. As Newton himself states the problem at the end of the Scholium, absolute space, he says this is a difficult notion. How do we deal with it since absolute space, as he puts it, does not strike our senses? Nevertheless, he says the situation is not hopeless, and that's why I wrote the book, to tell you how to figure out what the true motions are. So how can these concepts, absolute space-time and motion, especially as employed in the theory of universal gravitation, developed in Book 3 of the Principia, well after the Scholium, be as empirically successful as they in fact are, since they just don't have any relation to us, it seems. The Kantian answer, as later elaborated by Mach in the late 19th century concept of inertial reference frame, is that the Newtonian laws of motion implicitly characterize a privileged initial frame of reference, fixed, for example, at the center of mass of the solar system, within which the true or absolute motions described by universal gravitation are first well defined. Before that, we don't have absolute motion. We don't know what we mean. In this particular context, therefore, the notion of implicit definition leads to a genuine advance in conceptual clarification. And it is important to note that this is not simply a Hilbertian implicit definition of an abstract mathematical structure, as in Hilbert's axiomatization of Euclidean geometry, for example. Rather, it shows how an abstract mathematical structure, what we now call the structure of Newtonian space-time, actually corresponds to something in the empirical or phenomenal world. It does this by including not only abstract mathematical concepts, such as Hilbert's points, lines, and planes in his geometry, in the implicit definition in question, it also includes fundamental mechanical quantities as well, such as mass, momentum, and force. Newton's argument for universal gravitation in Book 3 then shows us how to measure these quantities empirically. Especially, it shows us how to measure the masses of the primary bodies in the solar system, so as actually to determine the relevant center of motion. We empirically compare the masses of the primary bodies in the solar system, as I just said, so as empirically determine its center of mass. This argument presupposes that both Euclidean geometry and the laws of motion are already in place. And it is in precisely this sense, in my view, that both Euclidean geometry and the laws of motion are constitutively a priori in Newton's theory. So Kant was right about that. He was just wrong, but that was the way it would always be. This kind of correspondence between mechanical concepts and empirical phenomena is quite different from the word-world correlations described by Wilson's atlas-like facade structures. It is not a matter of establishing local correlations between different patches of a theory facade and aspects of microscopic or physical reality, but of implicitly characterizing a global coordination between abstract spatio-temporal representations and concrete observable phenomena via what Reichenbach and others call coordinating principles. We do this in the case of Newton's original theory via the laws of motion, or in the case of special relativity via what Einstein called the light principle and the principle of relativity, or in the case of general relativity via an axiomatic characterization involving both light propagation and the behavior of freely falling bodies. The problems addressed by these kinds of axiomatic characterizations of spatio-temporal structure via coordinating definitions, principles, which are a kind of implicit definition, these problems are fundamentally different from those addressed by Wilson's atlas-like explanations of the patchwork behavior of microscopic physical concepts. In truth, the great conceptual revolutions leading from classical to 20th century mathematical physics through the extraordinarily rich intervening developments in both mathematics and physics of the 19th century involved both kinds of problems. Those involving the most general spatio-temporal form of physical theory, we might say, general mechanics on the one side, and those involving the particular kinds of matter interacting within this form on the other. Physics, both classical and post-classical, is essentially concerned with both problems. And a so far undeveloped area in history and philosophy of science would involve carefully studying the complex interconnections between these two sets of problems.